could show up. Obviously, we couldn't seat, I don't think, all 28 in this room if we wanted to. This room being what? The AT&T lab in the College of Technology at the University of Houston. And Mr. Phil Booth is kind enough to be putting this on Media Share, which you will have the good fortune to also experience May the 11th when you do your final presentations. On what subject? IPTV. Thank you. Another A for the class. Well, I'll talk a little bit about IPTV, of course, from my company's perspective. We do have UVerse. I thought Phil and I were talking about earlier, setting the room up, that maybe I shouldn't have that plane. Y'all might kind of divert your attention to the big screen up there. So my plan of attack tonight is to go over Dr. Stallings' material in our good book, or his good book. And what's nice about tonight's chapter? Kind of a loaded question. It does cover multimedia, so I thought this would be an ideal venue to discuss all the great multimedia things that are happening out there. And that's where technology is going, definitely in our network communications world. And just since this will be put on YouTube for an audience out there on the World Wide Web, a little bit about the College of Technology that many people aren't aware of. Just like you folks, most of you, I think, will be getting your bachelor's in network communications. You probably call it something else, though, don't you? But that's what I think of it next month, right? And how many of you are going to go for the master's in network communications? Oh, don't shake your head that way. Okay, well, some of you may think about it. Maybe now's not a good time when you're trying to get your bachelor's. But the University of Houston College of Technology is unique in that it does offer these two programs, one of the few in the country that does. So you're fortunate in that sense that it's right here in Houston. But then I've had the good fortune over the years, as you know, from reading the class syllabus. That's something I didn't bring out and put in front of me. The other good thing about tonight's class, as I wanted to finish, was this is the last chapter, the next to the last class. So you should all be excited about that. And for those of you that weren't here Tuesday, I did put up your homework assignment again. I think the TA may have posted it on the blackboard, not sure. But it is due Tuesday because we're having quiz review, right? And I know we'll have a full class Tuesday for that. That always tends to be the, well, very well attended for some strange reason. Anyway, because quiz will be next Thursday, the last quiz. And then, as I mentioned, your final presentation, May 11th at Studio D, is it called? Phil, over Studio what? 11D, okay. Anyway, the basement next to the UC on that side of the library. Can't miss it. Go downstairs and turn to your left. Not your immediate left. You'll get into Phil's office. But that's where my class is after this class in risk management. Okay, my goal tonight is to, maybe not quickly, but we'll see how the time goes, with Dr. Stallings' slides. And as you know, the material has its good and bad points sometimes, but I am obligated to cover it. So I wanted to at least get that out of the way before we get into some of the other nicer things in this room to talk about. And I will share with you some of that material that I picked up last Friday over at TLC Square on that wireless mobility workshop that was held. So, and that's really, you think the technology is moving toward internet protocol television. It's also moving on the wireless platform, as everybody in this class knows, because you've got a cell phone. Many of you have a smart device, right? I still have two cell phones, but neither one of them are very smart, and I kind of like it that way. Not one of these that want to be pestered all the time and feel like I have to respond to all the emails and everything. But anyway, I know I'm going to get probably an iPhone here one of these days because I hope to teach the class wirelessly. I know that's the way things are going, and I want to be one of the first ones to, you can actually do that if you go to HCC, Houston Community College. They were kind of the leaders in that area right here in our backyard. So, and they helped set up the workshop Friday. Anyway, that kind of leads into our subject matter tonight, right? Internet applications, multimedia. And let's get to slide 1. Well, actually, not a lot on this one. This is Stalin's typical for the birds, as I think he's got another thing on the birds statement up here, the human nature of birds. Anyway, I'm sure all this ties into multimedia somehow, but I haven't quite figured it out yet. But we're moving into the internet-based type applications. Multimedia obviously refers to multiple forms of information, not just your text messaging, which everybody does, which should be free, right? I probably need to edit some of these comments, Phil. Who knows what I'm going to pop off and say. But we've covered that material, or we've covered that aspect before. Very little bandwidth, right? But yet you pay a pretty good price to have that privilege. Of course, still pictures. I'm sure nobody sends pictures or photos on the internet, or audio. Nobody does voice communications, I'm sure. By the way, we do have, if you want to run around on the other side of the wall here, just put in for Sergio Chacon, the lab manager, who's nice enough, of course, to let me in here tonight to set this all up, because you notice he's not here. But we just put in a CVoIP, consumer voice over IP circuit for him. And right behind this one relay rack is down on the floor is your little battery backup unit for that residential gateway. So because of what? I think I mentioned this briefly last time. Yeah, not for your data or your video, but for 911 and emergency calling when the lights go out, because these are AC powered, so they could care less if you lose your video, just like if you had cable TV. I guess even your data for that matter. But voice is a little different matter. So actually, I think the backup time, somebody asked me that the other day, and actually I think it's more like 8 hours, because it doesn't take a lot of power to back that thing up. But after 8 hours, of course, here in Houston, that's probably not long enough for some of our events, such as hurricanes that happen from time to time. But even during Ike, our most recent one, I think, what did I say? AT&T provided like 3,000 backup generators for the equipment to keep that service up and running. So I think we were one of the few providers that did that. Okay, and video. That's obviously what we want to get into tonight. Actually, next Tuesday's class, we'll get into the characteristics of real-time traffic. Touch about on that, obviously, a little bit tonight, and that's primarily in the protocol SIP, Session Internet Protocol, or Session Initiation Protocol. Probably heard of it. So we'll get into that, like I say, in more detail. Before that, though, we want to talk about how it's important to compress not just, of course, audio, which isn't that big a deal, but the video. That's your bandwidth hog. So we need to go over a bit on how that is done, and to make most efficient use of the transmission capacity as possible. And we paid a lot of attention in the past to compression algorithms. However, tonight we're going to get into the Moving Picture Experts Group, MPEG, as I'm sure you've heard of it, under the auspices of the International Organization for Standardization, the ISO group. And they're the ones that have developed the standards over the years for video and audio in digital form. So the MPEG, as we'll say, effort covers not only the video compression, but like I said, the audio and associated system issues and formats. And what they were basing this on was an effort that the video signal can be compressed down to a bit rate of about 1.5 megabits. Now, today's world, you think, well, that's pretty slow. I can remember when that was considered pretty fast. That's a T1 rate, and that used to be a pretty, and still is in some cases, pretty expensive service. But I think, Chris, are you getting the 24 meg download now off you hadn't subscribed to that yet, but you're getting what? 6, okay. Well, that's a little bit more. That's 4 times 1.5. Yeah, I understand. Your wife still wants you to get a good job, right? So you can upgrade your service. Anyway, you're getting higher than that off cable, as I remember. Yeah, I know. We don't want to talk about that, do we? Okay. Sore subject. Anyway, he's going to introduce 2 terms. Data compression falls into lossless and lossy. With lossless compression, no information is lost, as you might expect, and the decompressed data is identical to the original uncompressed data. The efficiency of this type of connection I lost my place looking at our new student. Thank you. Is limited in the process of eliminating some or all the redundancy in a bit stream so that no information is lost. On the other hand, the lossy compression, the decompressed data may be an acceptable approximation according to some fidelity criteria to that original uncompressed data. And so we'll see how the lossy compression is used for both audio and video, but in the case of audio, that fidelity of the output is so high that for all practical purposes, the compression is lossless. People just don't want to have their voice chopped up and sound funny and everything else. But that really applies from a video standpoint too. You don't want to see crappy video signals either. So it reminds me of I had a note here to remind myself to mention, it reminds me of the plain old telephone service that some of you still have or know about, the landline as we refer to it, POTS line, that is basically a 3 kilohertz signal. And when you think about the human ear and the wide frequency response that it can pick up, that's obviously not much bandwidth for good fidelity. But way back when, Bell Labs said, no, actually for voice communications over phone line, that 3 kilohertz bandwidth is really pretty good. So there is, and Phil probably can relate to this, what we call a program circuit, and that bandwidth is from 15 to 20 kilohertz for your radio stations, for instance, because you want that high fidelity for orchestras and music, and there are audiophiles out there that are pretty sensitive to, not me, but other people that are sensitive to the low end and the high end. Of course, on the telephone line, there's this thing called 60 hertz from the power company that can come across and you can hear it on the line. Well, you don't really want that, so by designing the telephone line like they did, it pretty much factor that out of the equation, unless you just have a bad line and then you hear the hum. But that gets me into my old days in the telephone business. Don't have time to go into that tonight. A little bit more on simple audio compression. And as he says, the first step in the development of an audio compression algorithm is, of course, to digitize the audio signal using a technique such as PCM. You're familiar with pulse code modulation, right? Especially when we're talking about T1, same type of technology. Zeros and ones. It's important to note PCM or a similar technique does in fact provide a measure of compression. He said, recall back in chapter 5, I think that was your previous class, 4321 as a prereq to this class, 4325. Anyway, the sampling theorem states that if the signal is sampled at regular intervals of time and at a rate higher than twice the highest signal frequency, then the samples contain all the information of the original signal. so you don't lose anything. But to create that digital signal, each sample is quantized to a value that can be represented by a fixed number of bits, producing your pulse code modulation. And then your PCM encoded signal just produces only an approximation of that original signal. Now, if unlimited fidelity were required, then an unlimited number of bits would be needed for each sample. The fact that just a fixed finite number of bits is used per sample results in effect compression. So here again, taking the simple-minded approach, further compression could be achieved by reducing the frequency of the sampling or reducing the number of bits per sample. However, there is another approach that can produce significant compression and at the same time retain a fidelity that is equivalent to lossless compression, and at the same time attain a fidelity that is equivalent to well, as I just said, to lossless compression. And guess what that approach is? It's the MPEG standard, as he says, is quite complex, beyond our scope, but basically it provides for 3 layers of compression. And they call this layer 3, properly known as MP3. Anybody ever heard of MP3? Okay. Guess what that compression ratio is? 10 to 1. So that's pretty good for your little MP3 type player. Nobody has an MP3 player, I'm sure. Okay. A little diagram here on page 802, which kind of explains how audio compression takes into account the physiology of human hearing. The compression algorithm exploits a phenomenon known as simultaneous auditory masking. Greetings. I think the sign-in sheet's over there. When we run out of space, you'll probably just have to sit up front with me, see. No, we won't have you do that. Anyway, this masking is an effect produced by the way the human nervous system perceives sound. In essence, if 2 signals are sufficiently near to one another, one tone is stronger, the weaker signal is simply not perceived at all. The human hearing apparatus masks it. Thus, what the percipient hears is exactly the same, whether the weaker tone is there or not. So as this figure shows, at least in general terms, how we do that to encode audio signals. The input is partitioned into time frames ranging in duration from 2 to 50 milliseconds. Time frequency analysis module decomposes each frame. At the simplest, this module determines the amplitude in each of the sequence of narrow frequency subbands. More complex analysis algorithms are typical. In any case, the output of this module is a set of parameters that define the acoustic signal in that particular time frame and that can be quantized. And parallel to all this, a psychoacoustic module analyzes the time frame for masking effects and other properties that can be exploited to achieve compression. And based on this analysis, a bit allocation module decides how to apportion the number of code bits available for the quantization of the subband signals. So the resulting quantized signal is then fed into a lossless coding module that eliminates any redundancies in the digital signal to achieve maximum compression. Now the bottom figure basically shows the inverse operation of that in order to receive when you receive the other end of the signal. The unpacking module recovers the quantized signal by inverting that lossless compression, and then the resulting signal is processed to produce your audio output. That's for audio. What about for video? Well, moving picture, how many of you have, well, the old reels, the film, and if you looked at them, they're just individual frames, right? Individual pictures. Well, that's what video is when you get right down to it. So what? That, yeah, old-timey movie theaters. You'd have to, I don't know, are there any dollar theaters left anymore? Even those probably don't use those old reels. But yeah, I'm dating myself when I mention that. But well, you can still get your 8mm type. You just have to look at it. Some people don't want to pull the film apart and look at it. But It was easier to do on those bigger reels, but and then go through that little projection line. Anyway, the point is a moving picture is simply a succession of still pictures. So one can achieve a degree of compression by independently compressing each of these still pictures in that sequence, but much more can be done. When you think about it, the pictures, especially the ones that are adjacent to one another, is really the same content, right? So if you're moving, the camera, as we see here, is capturing my motion. Well, the background and all that hasn't changed. Only thing that's changed has been my movement. Well, that's all that has to be transmitted. Everything else basically stays the same. So that's how you can really get the pretty good compression ratios. With a lot of action, of course, it requires more, especially when you get into high definition type TV. We're really looking at some algorithms there to improve that quality. But this suggests that an encoding of differences between adjacent still pictures is a good approach to compressing video. And that's the tool used in MPEG. This is a little bit of description on how that's done. As we see here, the input to the MPEG compression module is basically a sequence of your video frames. Each frame is processed separately, being treated, here again, as a single still image. So while operating on that single frame, the MPEG order is in an intra-frame mode. And in this mode, the algorithm performs the following steps. You have preliminary scaling and color conversion. So each frame is converted into a standardized representation known as source input format, or SIF. And then the color information is translated into a scheme known as YUV. Then you do your color subsampling. And brightness is the dominant component of color that's seen by the human eye, while U, that's HUE, is less important. So the algorithm is able to reduce the U information by about 75% with little effort on subjective fidelity. Then we have what's known as a discrete cosine transformation, DCT, which maps each 8x8 block of points. And guess what that is called? Pixels. Anybody ever hear of pixels? Or if you've got UVerse, maybe pixelization. Anyway, we'll get into that shortly. But the more similar to a Fourier transform of that block. In essence, the DCT provides a frequency domain representation of the image. Then we get into the quantization. The DCT values are quantized into a finite number of possible values. So the more quantization levels that are used, the greater the picture fidelity. But the less the amount of compression. And then your full length your run length encoding. The quantized DCT values are represented using a run length encoding technique. And then finally, you have the Huffman coding. I think we talked about that once before. I talked about so many different people's names, I don't know if we talked about Huffman or not. The data stream is compressed using Huffman coding, which is a lossless compression technique that assigns the most common bit sequence from the preceding step to symbols that is as short as possible. Okay, here comes our sequence in the adjacent frames that we were talking about. Although significant compression can be achieved by simply processing a video signal as a sequence of still images, as we just talked about, the approach fails to exploit the considerable redundancy present in all video sequences. So MPEG studies indicate that an additional compression on the order of a factor of 3 by exploiting these redundancies in an interframe mode. For interframe mode, similar blocks of pixels common to 2 or more successive frames are replaced by what's called a pointer that references one of the blocks. So the major complication has to do with the order of the frames. Sometimes it is convenient to refer to a block in a preceding frame. Other times, it's convenient to refer to a block in a future frame. In the latter case, the encoder replaces the block with a pointer and also reverses the order of the frame. So you can see how this can start getting kind of convoluted. The decompression routine must put the frame back in the proper order prior to displaying it, or it's going to look garbled. Okay, this shows the interframe technique in a very general way. After the DCT and quantization phases in the processing of the frame goes through the reverse process at the end, dequantization, inverse DCT, in order to recover a frame that's identical to the one which will be recovered by the decompression algorithm. And then this frame is stored and used in the interframe mode to compare to succeeding frames. That didn't totally lose you. In designing the video compression algorithm, this MPEG study group identified a number of features that are important in order to meet the range of applications. And two are really relevant to this discussion tonight, which is called random access, which is a compressed video bit stream that should be accessible at any point in the sequence of video frames, and any frame should be decodable in a limited amount of time. This implies the existence of access frames, which are frames coded only in intraframe mode and that therefore can be decoded without reference to the other frames. Or the second one, which is the fast-forward reverse searches. It should be possible to scan a compressed bit stream and using the appropriate access frames, display selected frames to obtain either a fast-forward or a fast reverse effect. Nobody wants to do that, right? To kind of skip ahead, which is probably what I'll do when I view this later. Oh, I want to skip ahead to the good stuff. Anyway, the foundation of MPEG interframe compression is motion compensation. The idea behind this is that a portion of an image in one frame will be the same or very similar to an equal size portion in a nearby frame, which I just talked about. MPEG scheme makes use of two forms of motion compensation: prediction and interpolation. Well, talk about prediction. MPEG makes use of blocks of 16 by 16 pixels called macro blocks, in contrast to those 8 by 8 blocks I mentioned earlier in the DCT coding, to do this motion compensation. A frame processed in prediction mode is divided into macro blocks, each of which is encoded separately. This encoding is done with reference to an anchor frame that precedes the current frame. Kind of anchors the series of frames. Each macro block in the current frame is to be represented by a pointer called the motion vector to that macro block in the anchor frame that most closely matches this macro block. This motion vector gives the displacement of the macro block in the current frame with respect to its match in the anchor frame. And that, actually I could go back, but that was shown in that other previous slide. In this example, each video frame consists of 64 by 64 pixels grouped into 16 macro blocks. The shaded, well, I think I will. Whoop, I was afraid of that. Just as I say, I want to go back. Okay. In that upper 2/3. Got my pointer out here for a reason. Right in here, shaded portion. Is in the 16, well, it doesn't really label the axis, but in the XY position, 16 in the, well, I don't know if that's the horizontal or vertical, 16, and then one's in the 8. The match for this block in the previous plane is in position 24 and 4. The short arrow line in the left-hand frame represents this motion vector, which in this case is 8 and -4. Key aspects of predictive coding are that the matching macro block in the previous frame need not be on a 16-pixel boundary, and that the matching is not done against a previous source frame, video frame, but rather against a video frame that has been through compression and decompression. Having determined the matching block from the preceding frame. The MPEG algorithm records the motion vector and the prediction error, which is 16 by 16 matrix of differences between the current macro block, frame C, and the reference macro block in frame R. I don't even see that. But he did label the indexes there. Okay, let's go to interpolation. Although prediction results in higher compression rates than a simple frame-by-frame compression, more can be done. In particular, MPEG allows some video frames to be encoded using two reference frames, one in the past, one in the future. This approach is called bidirectional interpolation, resulting in higher compression rates than prediction based on just one reference frame. To see why, consider a scene that is moving at a rate of 1/2 pixel per frame. If we try to predict a macro block in the current frame based on the preceding or following frame, no exact matching block will be found. However, an average of the best match from the preceding and following frames provides an exact prediction, so that the error matrix is all zeros. This figure 24.3, I guess we already showed it, illustrates the technique used in bidirectional interpolation. The current frame, referred to as a B frame, is processed against two reference frames, one before and after this frame in time. Each macro block can be encoded using a block from the preceding frame, the forward prediction as it's called, the following frame, which would be the backward prediction, or one block from each reference frame. That would be your averaging, whichever gives the minimum error matrix. In the case of bidirectional interpolation, more information must be encoded. As with predicted frames, a matrix of differences is produced and then encoded using DCT. In addition, each macro block is encoded with an indication of the prediction mode, that forward, backward, or average, and then one or two motion vectors. Three types of frames are defined in the MPEG. Intra-frame, that's your I, which means encoded in JPEG style as an independent still image. Nobody's familiar with JPEGs, right? Predicted, that's obviously the P. That means encoded with reference to the preceding anchor frame. And then your bidirectional interpolated frame, which is the B we talked about. That's obviously encoded with reference to the preceding and the following anchor frames. The relative frequency of these types of frames within a video stream is a configurable parameter, must satisfy several trade-offs. First, there is a need to satisfy the requirements for random access and fast-forward reverse searches, as we just described. These requirements place a lower bound on the fraction of I frames in the encoded stream. Second, there is a trade-off between computational complexity and the number of B frames. More B frames means more computation. Finally, B frames can only be processed with respect to I and P frames. That is, one B frame cannot serve as a reference frame for another B frame. Therefore, the higher the fraction of B frames, the greater the average distance between a B frame and its reference, and the less the correlation between the B frame and its reference frames. Anybody still with me? Okay, a little bit on the frame order sequence here. The rules for encoding are as follows. Each I frame is encoded using intra-frame coding only. Each P frame is encoded based on the most recent preceding I or P frame, whichever is closest. Each B frame is encoded with the closest preceding and following I or P frames. Now, picture frames in MPEG are organized into groups. Each group consists of a single I frame, followed by a number of P frames and B frames. Because a B frame cannot be decoded until both its preceding and following reference frames are decoded, the members of a group are reorganized so that each B frame follows both of its reference frames. And this provides the example of that. The first 6 frames form a group. Frame 4 is stored after frame 1 because it is used as the forward prediction frame for your B frames 2 and 3, which are shaded, I believe. The frames 5 and 6 are then interchanged for the same reason. And then we get to frame 7, which is recorded as part of the next group because it is encoded after it is encoded after the iframe 8. Okay, a little bit about real-time traffic. Obviously, as we get more high-speed LANs and WANs, increase of line capacity on the internet and other internets opened up the as I was reading this last night. He says, opens up the possibility of using I-based networks for the transport of real-time traffic. Duh. Of course, this was written in 2007, but even back then, as I recall, at least voice over IP was still pretty popular. And like I say, that's just an app anymore. That's not that big a deal as it used to be. That used to be a pretty big deal. To me now, video, that's the big deal. Okay. And that ties in, of course, to real-time traffic as well. But he says it's important to recognize the requirements of real-time traffic differ, of course, as we know, from other applications such as your file transfer, email, and client-server applications, including the web. I mean, those things can, we like to say, maybe take forever, or when you're searching something, or you don't know if it's your internet connection that's slow, you don't know if it's the server that's slow. Anyway, it's not all that critical to the operation of your business or your social life or anything else. But if you're talking, that's a little bit more critical. You like to communicate clearly. And here again, video, of course, again, if you're watching YouTube and like in class in the other typical classroom, it hoses up and stops in midstream, and then I can't show you the full clip. That's kind of irritating. But, hey, you didn't pay anything for it. Now, if you're a UVerse customer and you're paying for the service, you don't want to have the Super Bowl, for instance, not play. Or, he's going for the catch to make a touchdown, and all of a sudden it freezes. That's not the time to have that kind of a problem, see. You may no longer be a customer. I mean, if you're not paying for a service, you sometimes tolerate these errors, right? I think you know what I'm talking about. Okay, so there is more of a concern. This has to do with the metrics of throughput and delay when we're talking about real-time traffic. Also concerned with reliability. Mechanisms are used to make sure that no data is lost, corrupted, or misordered during the transit. Here again, is really more dealing with timing issues. Most cases, there's a requirement that data be delivered at a constant rate equal to the sending rate. In other cases, the deadline associated with each block of data, such that the data are not usable after the deadline has expired. And he gives us an example on page 809 in figure 25.5. Here a server is generating audio to be transmitted at your typical 24 kilobits per second rate. The digitized audio is transmitted in packets containing 160 octets of data, so that one packet is issued every 20 milliseconds. These packets are then passed through your internet and delivered to a multimedia PC. You noticed how you had to throw in that word multimedia, which plays the audio in real time as it arrives. However, because of the variable delay imposed by the internet, it's in the intranet now. That is one difference with the UVerse service. That's AT&T's internal network. That's not the public internet. Big time difference. There's a lot of similarities, but it's our network. Anyway, this variable delay imposed by the internet, the inter-arrival times between the packets are not maintained at that fixed 20 millisecond rate at the destination. So to compensate for this, what do? Incoming packets are buffered, right? Delayed slightly, and then released at a constant rate to the software that generates the audio. So that especially if you're watching something, you know, that's why it takes a little while sometimes to download the application, and then it plays like it's okay. The compensation provided by the delay buffer is limited, however. Understand this, you need to define the concept of delay jitter, which is the maximum variation in delay experienced by the packets in a single session. For example, if the minimum end-to-end delay seen by any packet is 1 millisecond, the maximum is 6 milliseconds, then the delay jitter is 5 milliseconds. As long as the time delay buffer delays incoming packets by at least 5 milliseconds, then the output of the buffer will include all incoming packets. Of course, if the buffer delays packets only by 4 milliseconds, then in any incoming packets that had experienced a relative delay of more than 4, of course the absolute delay of more than 5, would have been discarded so as to not be played back out of order. This is a profile of the real-time traffic. Implies a series of equal-sized packets generated at a constant rate. Not always the profile of the traffic, as you might expect. This illustrates some of the common possibilities, such as continuous data source. Your fixed-size packets are generated at fixed intervals. This characterizes applications that are constantly generating data, have few redundancies, and that are too important to compress in a lossy way. Such as, he gives examples of air traffic control radar and real-time simulations. Then you have your on and off source there in the middle. The source alternatives between periods when fixed-size packets are generated at your fixed intervals and periods of inactivity. A voice source, such as in telephony or audio conferencing, fits this profile. Just as I'm talking, I'll be rattling on and then I'll stop, right? On and off. And then finally, your variable packet size. The source generates variable length packets at uniform intervals, such as your digitized video, which different frames may experience different compression ratios for the same output quality level. What are the requirements for real-time traffic? Low jitter would be nice, and low latency. I think we covered those terms before. Ability to easily integrate non-real-time and real-time services. Be adaptable to dynamically changing network and traffic conditions. As you know, the network out there does change, but for a lot of reasons. Good performance for large networks and large numbers of connections, such as a corporate type network. Should have modest buffer requirements within the network, should have a high effective capacity utilization, should have low overhead in header bits per packet, should have low processing overhead per packet within the network and at the end system. Now, these are difficult to meet in wide area IP-based network or the internet, and neither TCP nor UDP by itself is appropriate. So we'll see how that real-time protocol provides basically the answer for that problem. And I do believe that, well, we'll talk a little bit about that. Most of that will be Tuesday's class. Okay, a distinction needs to be made first between hard and soft real-time communication applications. What do you think soft real-time applications might be? And those are the ones that can tolerate the loss of some portion of the data. And then your hard real-time have zero loss. So obviously the video and the audio that we're just talking about versus the soft, which would be your emails or your web browsing or what have you. In general, soft real-time apps impose fewer requirements on the network, therefore permissible to focus on maximizing network utilization even at the cost of some lost or misordered packets. But in hard real-time applications, a deterministic upper bound on jitter and high reliability takes the precedence over your network utilization considerations. Okay, now we introduce SIP. I think I mentioned that at the start, which is your session. I thought it was initiation. I think I said, I don't know what I said. session initiation protocol. Application level control protocol for setting up, modifying, and terminating your real-time sessions between participants over your IP data network. Driving force here again was internet telephony, which is our voice over IP. SIP can support any type of single media or multimedia session, including teleconferencing. There's 5 facets, as he shows here, of establishing and terminating your multimedia communications. User location. Users can move to other locations and access their telephony or other application features from remote locations. That's pretty important. Availability, determination of the willingness of the called party to engage in communications. And then your user capabilities, determination of the media and the media parameters to be used. Then your session setup, both point-to-point and multi-party calls with agreed session parameters. And then your session management, including transfer, termination of the sessions, modifying the session parameters, invoking services. Various design elements, here again, based on the earlier protocols we talked about, obviously HTTP-like request, response, transaction model. Each transaction consists of a client request that invokes a particular method or function on the server and at least one response. SIP uses most of the header fields, encoding rules, and status codes of HTTP. This provides a readable text-based format for displaying the information. It also uses concepts similar to the recursive and iterative searches of your DNS. SIP incorporates the use of a session description protocol, another protocol, SDP. So you know in your quiz you're going to have to define all these acronyms, right? I was just seeing if you were still awake. Well, you'll find out Tuesday what will be on the quiz, right? You will be here Tuesday or in the other classroom. Not here. Don't come here. Anyway, session description protocol defines your session content using a set of types similar to those used in MIME. What does MIME stand for? Chris? Yeah, I know. That's pretty good. Close enough for government work. Okay. I thought this was the last slide. Next to the last slide. Of Dr. Stallings' material. So don't get up and leave just yet. We're getting to the good stuff. Wake up, Phil. It's coming. Okay, a SIP network can be viewed as consisting of components defined on 2 dimensions, your client server and your individual network elements. As you know, a client is any network element that sends the SIP request and receives the SIP responses. A server is a network element that receives requests in order to service them and then sends back responses to those requests, as shown in this figure. How some of the SIP components relate to one another and the protocols that are employed, such as your user agent, which resides in every SIP end station, your redirect server. I think he's got those defined up there. Used during session initiation to determine the address of the called device, which it returns to the calling device, directing the UAC to contact an alternative URI. This is analogous to iterative searches in DNS. And then your proxy server, which is an intermediary entity that acts as both a server and a client for the purpose of making requests on behalf of other clients. A proxy server, and I think we talked about this in the last class, primarily ensures that a request is sent to another entity closer to the targeted user. Proxies are also useful for enforcing policy. Proxy interprets and, if necessary, rewrites specific parts of a request message before forwarding it. Then you have a registrar, which accepts your register request and places information it receives in those requests into the location service for the domain it handles. And then your location service, used by a SIP redirect or proxy server to obtain information about a callee's possible location or locations. For this purpose, the location service maintains a database of your SIP address, IP address mappings. Okay, then your SIP servers and protocols. The various servers are defined as logical devices. They may be implemented as separate servers configured on the internet, or they may be combined onto a single application that resides in a physical server. The previous slide showed some of the SIP components. User agent acting as a client. Use SIP to set up a session with a user agent that will act as a server. The session initiation dialog uses SIP and involves one or more of the proxy servers to forward the requests and responses between the two user agents. User agents also make use of the session description protocol. I think I'll just go back to that slide. The proxy servers may also act as redirect servers as needed. If redirection is done, your proxy server will need to consult the location service database, which may be co-located with a proxy server and may not be. Then the communication between the proxy server and the location server beyond the scope of the SIP standard. DNS is also an important part of the SIP operation. Typically, a UAC will make a request using the domain name of the UAS rather than the IP address. Proxy server will need to consult a DNS server to find a proxy server for the target domain. SIP typically runs on top of UDP for performance reasons, provides its own reliability mechanisms, but may also use TCP. If a secure encrypted transport mechanism is desired, SIP messages may alternatively be carried over the transport layer security protocol, a TLS protocol. Okay, that's where I wanted to end with the formal material. Now let's get to the more informal material. If I can find it.
You mentioned that intranets, like you were saying, internet can better deliver packets in a specific order. Do they do that through some kind of quality of service?
Yeah. Oh yeah. There's don't get me to remembering what they are, but and I think we have our own set of acronyms for describing some of the. But and that has been refined and continues to be refined. I mean, they're coming up with all kinds of neat things. As you can imagine, and part of what we'll get into right now, and even describing the service into this location. In fact, it was just announced. I was reading a standard that came out on pair bonding. I think I've talked about how instead of just one telephone, two wires, one pair of wires to your house to deliver the service, which is usually about 25 meg of bandwidth. That by going with two pairs, I used to say the analogy was like a 4-wire data circuit, but now you can not only get higher bandwidth, they're saying up to 50 meg, but guess what? We can go further than that 3,000 foot limitation, which means we can just about serve everybody that wants it, finally. And the neat thing about it, which ties in with what I'm just getting into, they call it the iNID. You know what the NID stands for, right? Network, see, we got our own acronyms. Network Interface Device. That's the box on the outside of your house where, well, yeah, that's the DMARC. That's correct. Anything on your side is your stuff. That's the inside wiring. And then, of course, anything on the other side is telephone company property. Well, guess what the I in iNID stands for? Intelligent Network Interface Device. This is electronic devices. And not just that, but that's where your RG is going to be, or your, I guess essentially the guts of your gateway, because it'll also transmit wirelessly. It'll be like a Wi-Fi signal from that box to where we can avoid the inside wiring of the house. No more having to pull new Cat5 cabling and all this stuff. So it's going to increase the install time and hopefully improve the quality of service. So anyway, I just was reading about that today. I thought, all right, I just wished I could get it in Kingwood, which is not. Oh, that's another big announcement today. Anybody see who Century Telephone, or what I call CenturyLink, who they just bought? Quest. Anybody ever hear of Quest? Yeah, I know. Actually, they were that was one of the last of the old operating companies of the Bell system as we knew it. Basically, the western part of the western United States, headquartered in Denver. Now they're going to make the headquarters in Monroe, Louisiana. That's where CenturyTel is headquartered. I thought that was kind of interesting aspect. But do I? Yeah, the old Mountain Bell, Northwest Bell, Pacific Northwest Bell. And I think Nevada Bell was part of Pac Bell, part of California. That's AT&T. But they had like 14 states, western states. Arizona, New Mexico, yeah, the old Mountain Bell. And think about those regions. What are they? Are they highly dense like Houston, densely populated, or are they spread out? So, which is kind of like CenturyTel. They kind of serve the rural America. So it's probably a pretty good marriage. We'll see. But the essence of this, and actually leading into my slides here, I had to tease my former AT&T colleague that retired and now is working for, CenturyLink. I was going to say Embark, but that's what they used to be called up in Kingwood. And I said, hey, Bill. And of course, he already had heard it. That was the first thing that came out this morning, about 8 o'clock. I fire up the computer and I see that announcement. So he's the first guy I thought about it. But of course, the deal won't close and get impacted until second half of next year. So it's going to take a year to make all this thing happen. And I said, and they did mention the benefits of IPTV that they will be rolling out to more markets. And I said, I keep saying, okay, when am I going to get my IPTV? I know where the fiber node is down at the end of the street. I know I'm within 3,000 feet. I qualify for the service. But, Bill, I believe I will get UVerse. This is why I may have to have this edited film. I hope, keep my fingers crossed, I will be able to get UVerse, just like Chris does, at my home in Kingwood, delivered wirelessly through AT&T Mobility once they get into the 4th generation, which is next year, they're saying, or the end of this year. I mean, Sprint's already rolling it out here in Houston. So competition is really moving up things big time. So anyway, it's going to take that 4th generation wireless to deliver the bandwidth to deliver IPTV. But I'm not talking about wanting to watch it on my cell phone. I want to watch it on my big screen. I'll have my little femto cell or my, what are they calling it, microcell or whatever. And I'll still have my broadband connection. But anyway, hey, when you think about it, not only does that rule out that local telephone company, that means we can provide UVerse everywhere. So these old traditional boundaries, but that's one of the beauties of IP. You can really do a lot of neat things if it's an IP platform, and not trying to make this a sales pitch for AT&T, but we definitely have moved into the 21st century of being an IP type based company. And why? Because of this 3-screen strategy. By the way, here again, I might have to have this edited, but Quest and CenturyTel, guess what they don't have that companies like AT&T and Verizon have? A wireless company. Now, that doesn't mean they can't resell somebody else's service, like AT&T, like you do DirecTV or Dish or whatever. I'm sure we'll be happy to provide them that. But anyway, the strategy, and Verizon's strategy too, I'm sure, is to try to, although their Fios, their fiber to the home, is really more of a cable TV type of a platform. I'm not saying they can't do IPTV, but as you get into your project, doing an IPTV type application, and I think somebody in this class is going to be doing it from phone to phone, wireless phone to wireless phone? Or are y'all not here? Nobody acknowledged that, but I thought, now that is going to be a cool project. So I'm looking forward to that presentation. Anyway, I got off track a little bit, but this 3-screen strategy. Yeah, your big screen, let's say, in your apartment, that most of you are looking at, your PC, laptop, and then, of course, your cell phone, and marrying those 3, wherever you are. You probably have seen the commercials where somebody's watching a program and then has to go to a meeting or something, and he's watching, on his laptop, and then he has to put that up, so he continues it on his cell phone. But it's a little bitty screen. The screen sizes kind of shrink as you get down in technology. But IP all makes that possible. Well, and some of these slides are from that presentation I did on my Calhoun Lofts UVerse project. I think I've talked about before, where that was just back in August when that became available to everybody. The net, and you guys and gals are the net generation. I don't have to tell you that. Who was that comment last Friday's wireless workshop where they had a picture? They had gone out to the restaurant the previous night for dinner, and here they said a 1-year-old, looked like a 2-year-old to me, but they're sitting in a high chair playing with an iPhone. And somebody commented, probably checking their emails. Anyway, I don't know what generation that's going to be referred to, but just-in-time learning, all these neat things that I was thinking today. I got these 2 phones. One's company, one's personal. And one of the gentlemen on the presentation last week said, well, I got 3 phones. I guess he's got a business on the side or something. And I'm thinking, why carry 3 devices nowadays? And there's probably already an app that you don't need to carry 3 devices. You can have distinctive ringing, I call it, or distinctive signaling. So you know if the call is coming in as personal or whether it's business or whatever. So it might save you some money. Okay, a little bit about AT&T's IPTV service, and very little because most of you are aware of at least the architecture of it. I'll get specific on the diagram over there in just another slide here. But yeah, it's fiber-based. You got to, because of bandwidth requirements in delivering the service to a community. Think of it as I think I've talked about fiber to the node. Now, AT&T's strategy differed a little from Verizon's because they extended it all the way to the home, which is nice if you can afford it, but or at least they used to. I think they've kind of called that program off for some reason. But I'd like to have fiber to my home. But if you don't really need it, sorry, I might have messed up my mic. You don't really need it. If you need it, what's Google trying to do? Get 100 megabit? Or is it a gig? No, it was a gig. They were trying to get a gig to everybody's house. So, all right, fine. I'm sure one of these days we'll need that kind of bandwidth if you're willing to pay for it.